Okay, so multivariate optimization, like I think every other part of multivariate calculus that I've talked about, the first thing I need to say is you already know almost all of what you need to know from univariate calculus, because the important ideas are all from univariate calculus and they go through pretty straightforwardly. But as was the case with partial derivatives, second partials, there's a few little complicating things that come from having more than one variable. So we'll talk about those as we go through the process here. So a multivariate optimization problem would be something like choose x and y to maximize z, which would of course be a function of x and y. And just as in the univariate case, if you were just choosing x, the first thing you would do is you would write down the first order condition, and that would be taking the first derivative and setting it equal to 0. So we're going to do that same thing here, but we have to do it for each variable. Okay, so now we have multiple first order conditions, and I'm going to label them. So first one is going to be that the derivative of z with respect to x has to equal 0, and FOC2 would be the requirement that the derivative of z with respect to y equals 0. For however many choice variables I have, all the first derivatives of the objective function have to be equal to 0, and the reason is exactly the same as it was when there was only one choice variable. If any one of these derivatives does not equal 0, then you're not at a maximum point. If del z del x is positive, what that's saying is more x. You can get more z by increasing x. And if it's negative, it's saying less x. You can get more z by decreasing x. And that's true for every one of the variables. Okay, so the first thing we do is find all those first derivatives, set them all equal to 0, and use them to find the critical points, which we're going to call x star, y star. Okay. Find the points that satisfy all of the first order conditions. Okay, so we'll have as many equations as we have choice variables, and at each critical point, all those equations have to be true. As in univariate univariate optimization, the critical points might be minima, they might be maxima, or they might be saddle points. Okay, so they might be something else. And saddle points in multivariate calculus, some of them like really do look like saddles. Like there's a maximum in one dimension and a minimum in the other. You can kind of envision a saddle, but it's not really like the top of a hill or the bottom of a valley. It's a mix. Not all saddle points look like saddles, though. Really, just the definition of a saddle point is a point that is kind of tautological, satisfies the first order conditions, but isn't a local min or max. So that's not super important, but just a point of clarification here. So we have our critical points, the points for which all the first derivatives of the function are equal to 0. Now, the next thing we need to do is classify the critical points. Okay, so step 1 is to find the first order conditions. Step 2 is to classify them. And as in the univariate case, we're going to use the second derivatives to help us do that. But now we've got lots of second derivatives to manage here. So what we're going to do is we're going to organize those second partials into a matrix. Okay, the matrix gets abbreviated H. It's called a Hessian matrix. And this is what it looks like for the problem we're working on here. So here in the 1, 1 position of my Hessian matrix, I'm going to put the second partial derivative with respect to x both times. And over here in the bottom right corner, I'm going to put the other direct second partial. And here on the off diagonals, I'm going to have the, I wrote 2 there, but let's keep saying that as y's there. So second derivative with respect to x both times, second derivative with respect to y both times, and on the off diagonals, I have the cross partials. So in bigger problems with more choice variables, the Hessian would have the same basic shape. You'd have the direct second partials on the diagonal and the cross partials in the other places. So the Hessian matrix is always going to be symmetric with direct second partials along the diagonal there. Okay. We're just going to do a 2-variant example here in Math Camp. The generalization is pretty straightforward here. Okay, well, is there anything else I want to say about the Hessian? One other point I want to make before we go and actually say, well, what do you do to the Hessian to classify those critical points? The Hessian is that matrix of second derivatives, so they're going to be potentially functions of x and y themselves, but just as we can evaluate any derivative at any particular point, we can do that for the Hessian too. So we could say the Hessian evaluated at, for example, x star, y star would just be xx at x star, y star, fxy at x star, y star. Same thing here, xy. Okay, so we can plug in values to all those functions that are in their various places in the Hessian matrix and turn the Hessian into a matrix of numbers if we want. All right. So here, so let's get back to kind of the main narrative here. We've found our critical points x star, y star. Okay, so we're going to assume that x star, y star satisfy the FOCs. Okay, so that's saying that the first derivative with respect to x at x star, y star is 0, and the first derivative with respect to y star evaluated at that same special point, x star, y star equals 0. Now, let's think about what's going on with the second derivatives at this particular point, x star, y star. Okay, so if x star, y star is greater than 0, and the determinant of the Hessian at x star, y star is also greater than 0, x star, y star is a local minimum. I'm going to write out 3 things, and then I'm going to sort of talk through the details. If that same first derivative with respect to x both times, x star, y star is less than 0, and the determinant of the Hessian, also evaluated at x star, y star, is still greater than 0, then x star, y star is local max. And third, if the determinant of that Hessian at that critical point, x star, y star, is less than 0, x star, y star is a saddle point. Okay, so let's step back and think about this. Let's remind ourselves of what determinant is. I said in Unit 9 that they show up all sorts of crazy places, and here's one. The determinant of H is the determinant of matrix that looks like this. I'm not putting in the points here because I just want to remind you about taking determinants. Okay, to take the determinant, we multiplied the on-diagonal elements and then subtract off the off-diagonal elements. Okay, so it's f x x, f y y, on-diagonal elements, minus f x y squared, relying on the fact that the Hessian is symmetric because those cross partials are the same. Okay. So that Hessian has to be positive for us to be at either a min or a max. If the Hessian is negative, doesn't matter what the signs of the derivatives themselves are, we're at something that's not going to be a local extreme value. If the Hessian is positive, though, then we look at the sign of one of the direct partials. And you might be thinking, well, like that's weird that we have xx in here and we don't have fyy. But if you look at the determinant formula here, if this is going to be greater than 0 and we're subtracting off a squared thing, the only way this is going to be greater than 0 is if the two direct second partials have the same sign. Okay, so let's put that out. Can only be positive f xx and fyy have the same sign. Okay, so if it's bugging you that we have fxx here and not fyy, we could write it as fyy, and then the fact that fxx would have to have the same sign would be implied. So really what this is saying is if both direct second partials are positive and the determinant is positive, we have a local minimum. If both direct second partials are negative and the determinant is positive, we have a max. Okay, so this first part, that the direct second partials are positive, that's the same as in the univariate case. If the second derivative is positive, we have a local min. If the second derivative is negative in the univariate case, we have a local max. In the multivariate case, if all the direct second partials are negative and the determinant is positive, we have a local max. Okay, these conditions are sufficient conditions. If they hold for a critical point, you know what that critical point is. If they don't hold, like if the determinant is 0 or those direct second partials are 0, it's inconclusive. You'd have to go to some other kind of tests, and there are other kinds of tests. Some of them are in chapter 13 of Sid, Sater, and Hammond. You might want to take a look there, but this particular set of second order conditions I think is going to get you through the kind of examples you're going to encounter in your methods classes or your formal theory classes. Okay. So next lesson will be a little example working through this in the context of a specific problem. So I'll see you then.